12.3 Gas and Temperature Change. Gases and temperature change. So the temperature of a substance is defined as the measure of the average kinetic energy of the molecules in that substance. So for an object to give off warm temperatures, it's because the kinetic energy is very high. Okay, so if the kinetic energy is very low, it will not have as high of a kinetic energy. It won't have that kind of movement. Okay. So temperature and volume, the scientist involved here was Jacques Charles, or just worry about Charles. I don't care about any of the dates on the multiple choice. I never give that kind of stuff, so don't worry about the dates. But the thing is, he looked at temperature and volume. Remember, Boyle looked at pressure and volume. Charles, on the other hand, is looking at volume and temperature. But now if you stop and think about temperature, you've got to understand that temperature can be kind of ambiguous if we're using temperatures like degrees Celsius, or we're using temperatures like degrees Fahrenheit as as some other parts of the world use. And one of the problems with using temperature is the fact that we actually can have a negative value. Okay, so using negative values can be very ambiguous, because all of a sudden, if we use a negative value in a question, we're going to get a negative volume, negative pressure. We're going to get a negative, so that negative can add some ambiguity to our question. So we need to be able to convert our temperature to a number that is going to prevent us from losing sight of that positive negative relationship. And here is what we come across from Lord Kelvin, scientist, who discovered that at minus 273 degrees Celsius, all molecular motion would cease. So at this temperature, the kinetic energy would be considered zero. And if the kinetic energy is considered zero, then hypothetically, the volume of the gas would be zero, which means we no longer have a gas, and now that gas has become a liquid. Okay, so we use this, what's referred to as the absolute zero, and we're using what is referred to as the Kelvin scale to make sure that any time you're being asked to use temperature in your calculations, you are to always use the following equation. Okay, so the temperature in Kelvin is degrees Celsius, whatever the degrees Celsius, okay, plus 273. Okay, and this will prevent us from getting a negative value for temperature, because the smallest value for temperature, if we use the Kelvin scale, is 0 Kelvin. And at 0 Kelvin, technically, we don't have a gas anymore. And because according to this graph, that we assume that the volume is 0 of a gas, which means we don't have a gas anymore. So remember that. Anytime, every time. Remember this. So here's the note. Anytime you are dealing with temperature in a calculation, always, always, always use this formula. Okay? I don't care if the question says, give me the answer in degrees Celsius. You still convert it to Kelvin to use the formulas, and then convert it back. Okay? You convert it back to get it to degrees Celsius. So what you're going to do is you're going to take that Kelvin value, okay, so whatever that Kelvin value, let's say it's 373 Kelvin, and you want to convert that to degrees Celsius. Well, you subtract it now by 273, and that'll work out to 100 degrees Celsius. I tried to calculate something that was really quick. Okay, but it's really cool actually. If you kind of play around with the temperature on Google, you can actually get Google to tell you the temperature for the day in Kelvin. But it doesn't really make any sense to us, right? Think about today. The temperatures hit as high as like 30 degrees. Okay, so if we put 30 degrees in here, we would get a value of 303 Kelvin. Doesn't really make any sense, okay, to us. Let's say when the temperature is at 0 degrees Celsius. Well, the temperature is 273 Kelvin. To us, we don't know how to dress, right? But if we do it in degrees Celsius, because we understand degrees Celsius, I know, hey, at 0 degrees Celsius, hey, I'm going to put on a jacket. Okay, I might put on maybe a coat. But in Kelvin, Kelvin is used to prevent any negative values being used in calculations. So Charles' law saw the following relationship, that volume was directly proportional to temperature if the pressure was kept constant. So if the pressure is kept constant, Charles' law looks at volume and temperature, with pressure being remained constant. Now notice here, this is a direct proportionality. So what does this mean? It means that if volume goes up, so will temperature. If volume goes down, so will temperature. Okay, which is different from Boyle's law, which was an inverse proportionality. Okay, so Charles' law is a direct proportionality. Okay, direct proportionality between their sets of units. So there, the Charles's equation is as such: V1 over T1 is equal to V2 T2. My advice for the final evaluation is to have these equations handy when you are doing any of the problems. So have these equations handy so that you're able to refer to them for the culminating evaluation coming up next week. So, as he stated here, so we're not exerting any pressure. Remember how in Boyle's law we were exerting pressure? So the pressure is the same, right? It's just the air around us, okay? But what happens is we have a flame, and we heat it, so it gives rise to a specific volume. We decide to increase that temperature, so we're increasing the temperature, right? We're creating the flame to force the temperature to increase. All of a sudden now the gas molecules are going to expand the volume of the container, right? So, and it makes sense, right? As temperature went up, so did the volume in this example. Now, next scientist that we're going to look at is Gay-Lussac, and Gay-Lussac is again reminding everyone that the volume of a container is the volume of the gas. But now he, on the other hand, looked at the pressure and temperature of the gas when volume remained constant. And the volume was whatever the container that it's in. That volume isn't changing. So the container is a set shape. It's got a gas in it. We're going to exert pressure on it. Okay? But we're going to change the temperature. How is the pressure going to change? And so he's come up with the following equation. P1 over T1 is equal to P2 T2. Okay, so notice here we're looking at pressure and temperature, while in Charles's law we were looking at volume and temperature. Okay, so difference. But again here, because we're looking at pressure and temperature, here volume is constant. So, which means also has the same proportionality, okay, proportionality as volume, as Charles's law. So as pressure increases, so will temperature. As pressure decreases, so will temperature. Okay. So we've got some sample problems with the answers that you can find at the end, but we're going to just kind of quickly skim through so that you see exactly how to go about starting these questions. Okay, so again, as I mentioned, start off by listing the information. So we've got a V1, we've got a T1, a T2, but the question asks, what volume will the oxygen occupy? That's our V2. So we think back, which one of the formulas are we using? We're using Charles's law, V1 T1 equals V2 T2. Okay, again, remember, anytime we are dealing with temperature, I don't care the fact that it's at 20 degrees Celsius and 65 degrees Celsius, you still need to convert them to Kelvin to use in these calculations. Even though they're not negative values for temperature, do not ever, 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 I am telling you now, I'm warning you ahead of time, these will all be wrong if you keep temperature as degrees Celsius. Okay, and if you're using Fahrenheit, same thing. You're going to get wrong answers. They're not going to make sense. You can test it out by putting degrees Celsius as temperature units. You are not going to get the same volume. Be aware, there's no need to change the volume. And here I'm asking, it's in centimeters cubed. Keep it as centimeters cubed because nowhere in this question do I ask you to change it into any other specific volume. Okay, so as I said, there is no need to convert centimeters cubed to liters because typically people know units as liters or milliliters. Centimeters cubed is fine. Doesn't ask for it. Okay, second sample problem asks for the same thing. The difference is it's asking us for the temperature in degrees Celsius at the end. So what we do is once we get our answer, don't round that yet. Don't round it. Throw it into the Kelvin formula to convert it back to degrees Celsius. Okay, and that's where we're getting now a negative value in this example here. Okay, and the last one here, we're looking at Gay-Lussac's, right? And how can we tell? Well, once we do this, if we take the time to list the units, you will see exactly which one of the formulas. You look at it, go, okay, I got P1, T1, P2, V, T2. Which one of the formulas am I using, right? That's why I said have those formulas available to you so you can look at them and go, oh, I've got P, I've got T. There's no V, so I'm not using Boyle's law, okay? There's no V at all, so I'm not going to be using Charles's law. So here I'm only using Gay-Lussac's law to answer this question. And again, notice degrees Celsius to Kelvin. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.